Our next presentation is from David Bryce from the Department of Chemistry and Biomolecular Sciences at the University of Ottawa. One of Canada's most creative and prolific physical chemists, David Bryce is an internationally renowned authority on nuclear magnetic resonance, spectroscopy, and electrophilic interactions in solids. His paradigm-shifting discoveries in the analysis and interpretation of spectral data have led to breakthroughs in our understanding of solid materials, pharmaceuticals, and biomolecules. An inspirational mentor, Professor Bryce is also known for bringing a passionate voice to the national discussion on science funding priorities.
My name is David Bryce, and I'm the University Research Chair in Nuclear Magnetic Resonance at the University of Ottawa. My work is in the field of NMR spectroscopy. Several Nobel Prizes have been awarded for developments related to NMR spectroscopy. Edward Purcell, the Nobel Prize winner in physics in 1952, said in this quote from his discovery, "There the snow lay around my doorstep, great heaps of protons quietly processing in the Earth's magnetic field. To see the world for a moment as something rich and strange is the private reward of many a discovery." What is this delicate motion he describes, and what are these great heaps of protons quietly processing? Well, as many of you will know, subatomic particles like protons and electrons possess an intrinsic angular momentum known as spin. In an applied magnetic field, perhaps a strong one or perhaps a weak one is the Earth's own magnetic field, the nuclear spin angular momentum will precess in a manner similar to a spinning top as shown here. And in fact, the rate of this precession is very sensitive to the surrounding molecular and electronic structure and can tell us everything about the structure of the molecule and more. This is the same phenomenon used in MRI. Pour les protons, le taux de cette précession dans un champ magnétique terrestre n'est que 2 kHz. Mais pour diverses raisons pratiques, notamment la sensibilité et la résolution, il est souvent souhaitable d'utiliser les champs magnétiques appliqués les plus élevés que possible pour les expériences RMN. Les champs magnétiques utilisés généralement de l'ordre de 10 à 20 Tesla dans des fréquences de précession dans la région des radiofréquences du spectre électromagnétique, c'est-à-dire des centaines de mégahertz. In fact, it's not uncommon for local radio stations to show up as interference when attempting to record NMR spectra, as these share the same range of frequencies. At the University of Ottawa, we typically use magnets which cause protons to precess or resonate at about 200 megahertz and up. Shown here is a 900 megahertz magnet, which has been housed at the National Ultra-High Field NMR Facility for Solids in Ottawa since 2005. Almost every element in the periodic table has a nucleus which possesses non-zero nuclear spin angular momentum. So this means that we can use the method to explore and understand the chemical structures of all different classes of molecules and materials, including proteins, catalysts, battery materials, and more. My lab has developed experiments to understand and exploit the electronic communication between different nuclear spins in a molecule. In a given molecule, any pair of spins can in principle communicate with one another, thereby affording long-distance information on the molecular structure. And by piecing together this information from different parts of the molecule, a fuller picture emerges. Understanding chemical structure is always key to understanding properties and potential applications of molecules. Here's a simple representation of some spectral data along with two molecules, which demonstrates just one simple application of our work. At left, we have two spectral peaks separated by a particular value labeled here as 3J. My student Fred Perra showed that this factor of 3 arises due to the inversion symmetry in the middle of the boron-boron bond in the molecule shown below the spectrum. Conversely, when that symmetry is broken, in this case through a chemical reaction, the spectral splitting collapses to J on the right. These experiments thereby provide a very useful and sensitive probe of crystallographic symmetry. One of the other areas my group has explored is that of pharmaceutical polymorphism, which, as we know, is a multi-billion-dollar industry. And one of the strengths of the NMR methods we've developed in my group is their sensitivity not only to the molecular structure of a compound, but also to the manner in which individual molecules stack together in a solid. Many molecules, including pharmaceuticals, exhibit polymorphism, where the same pure compound can arrange itself differently in the solid state depending on how the crystal or powder or pill was prepared. This phenomenon has enormous implications for the pharma industry, where each polymorph can be uniquely patented. Our work has been used to help resolve competing claims in the pharma industry by using NMR to unambiguously identify various polymorphic forms of active pharmaceutical ingredients. One of the main reasons for polymorphism is the fact there's various competing weak interactions between molecules. In our work, we have used NMR to characterize and understand a developing subset of non-covalent interactions known as sigma hole interactions. One example shown here is the halogen bond, where a halogen, in this case iodine, shown in purple, interacts weakly with a nitrogen atom, shown in blue, on an adjacent molecule to influence the overall arrangement of molecules in the crystal lattice. The example shown here depicts a method which can rapidly identify the presence of such interactions in a matter of seconds. Up until now, I've been mainly talking about the structure of molecules in crystalline solids, but a closer look reveals that there are many dynamic processes which are absolutely critical to their properties and applications. If we consider a solid crystal, you may think that there are molecules or parts of, you may not think that there are parts of molecules which are undergoing dynamic processes at a substantial rate. We've developed and applied NMR methods to better understand such processes in various chemical reagents, materials, and catalysts. One particularly exciting example was the demonstration of the role of the non-covalent halogen bond in catalyzing molecular dynamics in solids. This could have interesting future applications in the development of improved molecular machines. I'd like to thank you for your interest and thank my research group for their contributions over the years.